Good evening everyone. My name is Devlina Maiti. I am a NPTEL TA for the course Basic Real Analysis and the course instructor is Professor I.K. Rana. So in this session we are going to discuss about partial derivatives and maxima minima of a two variable function. So let's wait for 5 minutes and then we'll start this session. Okay, so let's start this session. So if f is a function from R to R, one second. So for a function from R to R, the derivative is defined by limit h goes to 0 f of a plus h minus fa by h. If this limit exists, if this limit exists, then we say that f is differentiable at the point a and it is defined by f dash a. Then f is differentiable at x equals to a and f dash a equals to this number. Right. Now in real line, for this a, we can approach a from only these two direction, from left or right. So there is only two direction, and when we are saying that h goes to 0, this means h can go to 0 from left side and right side. So if these two limits, h goes to 0 plus and h goes to 0 minus, exist and they are equal, then this limit h tends to 0, this limit exists. Both the limits must exist and they has to be equal, right? If they are equal, then this limit exists for these two directions. Now if f is a function from R2 to R, then, and let's say AB belongs to this R2, here this A belongs to R. So there is, suppose this is the point AB, right? So since AB is a point in this plane, then we can approach AB from any direction, right? From a direction parallel to the x-axis, parallel to y-axis, some other directions, right? So there are infinitely many directions to approach AB in this plane, right? So if we then for a single, now suppose we are approaching AB from the x-axis, from parallel to x-axis, like this one. So here this is AB and we are approaching in this direction, this in the parallel to x-axis, right? Then what is the differential? So for f from R2 to R, if this limit h goes to 0, so what is this number? This number was, this was f of a plus h, the point plus a number h which goes to 0, right? Similarly here the point is AB, so this is this point plus h, a small number. So here it was f of a plus h. So in real line the unit is 1, right? The unit number is 1. Now if we approach AB from x-axis, the unit number is, unit vector, the unit point is 1 0, right? So here h into 1 0 minus f of that point, f of a, this means f of AB, right, by h. So if this limit exists, so this actually, this limit is what? This is actually a plus h b minus f of AB by h, right? So if this limit exists, then it is called the partial derivative of f along x-axis, right? And it is denoted by this fx, or you can write del f del x, right? So here it was f of a plus h minus f of a. Here the point is AB, so the point is AB plus h into the unit vector h into the unit vector along which we are approaching AB. So here we are approaching along x-axis, right? So that's why this is h into 1 0. 1 0 is what? 1 0 is the unit vector. So here 1 0 is the unit vector of x-axis here in R2, and here 1 is the unit point in R, right? And there is only the x-axis, only a single line. So this is called the partial derivative of f along x-axis, and it is denoted by fx or del f del x, right? Now similarly, the partial derivative along y-axis is what? So if limit k goes to 0, f of AB, the point, plus a small number k into the unit vector along y-axis. Now unit vector along y-axis is what? This is 0 1, right? So k into 0 1 minus f of AB, the point, by k. So this is nothing but f of a b plus k minus f of AB by k. So this limit, if this limit exists, then it is called the partial derivative of f along y-axis, and it is denoted by fy f suffix y or del f del y, right? So this is the partial derivative of this f along y-axis. Now there are infinitely many directions in R2 to approach R. So let's take U to be a point, suppose PQ. Right. So here is our AB point, and we are approaching AB along the direction of PQ, right? So suppose PQ is here, so this is suppose PQ. So the direction of PQ is this one. So this is the PQ direction. Now if we do the parallel line parallel to PQ, so this line, so we are approaching AB along this line parallel to PQ, right? So this, so this line means we are approaching AB along x-axis, parallel to x-axis, and this line is this is along y-axis, parallel to y-axis, and this one is along u, along the direction of PQ, right? So along this side, so we'll say the derivative of f along this side is what? This is the directional derivative. So this is also called directional derivative of f. So so along u, so limit h goes to 0, f of the point AB plus a small number into the vector into the direction, right? So direction here is u, so it is PQ minus f of AB by h, right? So here u is this number. So this limit, this is called the derivative or the directional derivative of f along the direction u, it is PQ, right? This is called the directional derivative of f along this direction u, right? Now if fx, fy exists, the partial derivatives, then we can again do the higher derivatives, that is fxx and fxy, fyy, right? All those four terms. So if fx, fy exists, then we can go for the higher derivatives. Then we can define in a similar manner, define the second order partial derivatives fxx, fxy, fyx and f of yy, right? Now what is fxx? fxx of AB, suppose. So what is this function? So this is limit h goes to 0. Here the function is fx of a plus h b. Since this is xx, this is x, so we are approaching fx, the function at the point AB, through x-axis. So fx minus the function is fx by h, right? Similarly, if it is xy, then it is limit k goes to 0, fx a b plus k. Now we are approaching fx a b along y-axis by k. And similarly, fyx a b is the function is fy and we are approaching by x-axis, so it is a plus h b this is x, so and similarly the last one fyy is k goes to 0, fy, the function is fy a b plus k, right? Okay, so we'll see some examples. Okay, when is f of xy and f of yx is equal? So they are not actually equal in general, but if they are continuous in an open domain, open set, then they are equal. So this theorem says if fxy, fyx are continuous in an open set containing this point AB, then fxy at this point AB equal to fyx at this point AB. So if they are continuous, then they are equal. Okay, we'll see some example. You have to calculate this fx, fy for a function. So take this function fx equals to sin 3y plus 5x minus 6y. Right. Now what is fx for any xy? So fx is actually what? This partial derivative, what we have written? F of a plus h minus b minus f ab by h. So this means we are just differentiating f along x by fixing this y, right? When we are doing the partial derivative of f along x axis, that is we are calculating fx, then we are keeping y fixed, right? So this means this fx will be what? Will be 4x cube. This y is as it is, so y will act as a constant here, right? So 5, right? For general fx at the point xy, right? So we are just differentiating with respect to x, keeping y fixed. Y is a fixed number, arbitrary, but here y, when we are doing the partial derivative along x, y is fixed, right? Okay, let's look at the second. So fx is this and fy is right. Now for 2, let's take fx to be, fx is log of 1 plus xy and we have to find fx 0 0 and fy 0 0. Okay, so what is fx 0 0? By this definition, this is limit h goes to 0, f 0 0 minus, sorry, f h 0 minus f 0 0 by h, right? This is by this definition, this one. Okay, so what is this value? h0 is 0 and f00 is also 0 log 1. So this means fx00 is 0, and similarly this is k goes to 0, f of 0k minus f00 by h, which is again 0, right? So fx00 equals to 0 and fy00 is also 0, right? Okay, let's go to the next problem. So our fx is given by y x square minus y square by x square plus y square whenever xy is not 0, and 0 when xy is 0. xy 0 means when x and y both are 0, then it is 0, right? So we have to find what? We have to find if x, if y, if xy, if xx, x, if yy at 0, 0. So you have to find all these partial derivatives of first order and second order at the point 0, 0. Okay. So first let's find the partial derivative with respect to x. So what is fx00? This is h0 minus, right? So since y here is 0, so from this from the definition of fxy, it is actually 0. Y is 0, so it is 0, and f00 is given by 0, so this value is 0. And what is fy00? f0k minus f00 by k. Now 0k is not 0, so 0k is k minus k square by k square minus f00 is 0 by k, so which is nothing but minus 1, right? So fy00, so what we have found? We have found till now fx00 equals to 0 and fy00 is minus 1, right? Now we have to go for second derivative. So first we will find fxx00. So what is this? This is h goes to 0, fx of h0 minus fx of 0, 0 by h, right? So to find this, first we have to find fx h0 and fx00. fx00 we have already found. So now what is fx h0? So what is fx h0? This is h1 goes to 0, f of h plus h1 0 minus f00 by h1, right? By the definition, limit definition. Now what is this value? Now since here y is 0, by this functional value, this one is actually 0 and f00 is 0, so its value is 0. So from 1 now, from 1 using the previous value, we get we get what? We get fxx00 equals to limit h goes to 0. Now fx h0 is 0 and f00 is 0, so it is 0. So we have found that fx00 is 0, and the remaining is fxy, yx and yy, right? So let's find fxy 00. So it is k goes to 0, fx of 0k minus fx00 by k. So you have to find fx0k and fx00. I think fx00 is 0, so it is goes to 0, fx0k minus fx00 is 0 by k. Now what is fx0k? Equals to h goes to 0, fhk minus f0k by h, right? So fhk is k times h square minus k square by h square plus k square, and f0k is minus k cube by k square, right? And this is divided by h. Now if we simplify it, we'll get h goes to 0 and it will be 2h k by h square plus k square, right? So since h goes to 0, k is fixed here, so this is 0, right? Because k is fixed here and h goes to 0. So fx hk is 0. This implies fxy00, which was limit k tends to 0, fx0k by k. So since it is 0, so it is also 0, right? By this formula. So fxx, fxy is done. So you have to find fyx now. So it is h goes to 0, fy h0 minus fy00 by h. So we have to find fy h0, right? Because fy00 is minus 1. Fy00 is minus 1. So you have to find fy80, which is what? K goes to 0. So we are using the definition again and again, right? So this is fhk minus fh0 by k. So fy80. So it is fh0 is what? Since y is 0, it is 0 by k. So it is actually h square minus limit k goes to 0 square minus k square by h square plus k square. Since k is 0, it is 1, right? Since k goes to 0, this value is 1. So from this value, fyx00 now is what? Equals to h tends to 0, this is 1 minus of minus 1 by h, right? So this gives 2 by h. Now since h tends to 0, this goes to infinity, so this limit does not exist. So this does not exist. This means fyx00 does not exist. Right? And we have if this one, if xx, fx and fy, and we have to calculate fyy. This is the remaining part. So you have to find if. So you have already okay, we have to find fyy00. So this is k goes to 0, fy 0k minus fy00 by k. fy00 is what? fy00 is minus 1, right? So fy00 is minus 1, this is divided by k. So you have to find now fy0k. Now to find fy0k is limit k1 goes to 0, f of 0 k plus k1 minus f0k by k, right? So this is limit k1 goes to 0, and this value will be this is minus k plus k1, because this from this definition, this if x is 0, it will be minus y, so this is minus k plus k1, and similarly this is minus k by k. So it is k1, so this implies this will be minus 1, right? fy0k is minus 1, so if yy00, since both is minus 1, so it is minus 1 minus of minus 1 by k, and this is 0. So fy yy00 is 0. So we have found all the 4 partial derivatives and the 2 of first order partial derivative and all the 4 second order partial derivatives, right? Okay, now we'll discuss about maxima minima of this 2 variable function. Okay. Maxima and so we'll start with a theorem. So I've already written a theorem. So let a subset of this R2, right? If the maxima or minima of this function f from R2 to R occurs at a point AB. So AB lies in the interior of this A. In the interior of A, and fx, fy both exist, then fxab equals to 0 and fyab equals to 0. Right. If their maximum, this is a necessary condition, if this maximum and maximum or minimum occurs at this point AB, then the partial derivative of f is 0. Okay. But the converse is not true. If the partial derivative at a point is 0, does not imply the point will be maximum or minimum. So that value may not be an extremum point. Okay, so we will see the converse is not true. So first example we will take in R. So if we take fx equals to x cube, then f0 is 0, right? But this 0 is not maxima or minima, local, it is not local maxima or minima. Why? So this is 0, and how does it look like? So x cube is this one, this is 0, right? This is y equals to x cube, this graph, right? So you see that if we take a small neighborhood of this 0, there are points where fx is positive and negative, right? Because if we take this, any neighborhood of this, at this point this is positive, and at this point this is a negative value, right? So if it is a local maxima or minimal, it is local maxima means there is some neighborhood where this value of 0 is the maximum value, right, or minimum value in that neighborhood. But in each and every neighborhood of 0, there are some points where it is positive, and also at some point it is positive, and at some point it will be negative value. Fx, the value of f will be negative or positive. So 0 cannot be maxima or minima, right? So you see that here f dash x, so f dash 0 is 0, right? But 0 is not a maxima, local maxima or local minima, right? Again, if we take in R2 this fxy, if we take x square minus y square, right, then we see that all the partial derivative fx is what? Fx is 2x and fy is 2y minus 2y. So fx at the point 0, 0 is 0, and fy at the point 0, 0 is also 0. But this 0, 0 is not a local maxima or minima. This is not an extrema in a similar manner. So this is this point, right? So this is 0, 0. Now we are approaching 0, suppose in x-axis. So we approach x from x-axis. So then y is 0, right? So what is the value of f? Now if we approach 0, 0 from x-axis, so y is 0. So then if x0 is what? If x0 is minus y, if x0 is x square, right? And if we approach 0 0 from y-axis, this axis, then x is 0 in this axis, so f0y is what? F0y is minus y square, right? Now if we take any neighborhood of this 0 0, suppose this neighborhood, right? So if we take any neighborhood, there are points in x-axis, so there are point in x-axis, also in y-axis, right? In any, if we take any neighborhood of 0, there will be points some in x-axis and y-axis. Now in the at the points of x-axis, it gives positive values, x square which is greater than 0, and at the points in y-axis it gives negative value, right? It is not 0, so it is strictly less than 0. So in each of this neighborhood there are points which is positive and points which is negative in each neighborhood of 0 0. So 0 0 can never be a maxima or local minima, right? So in each neighborhood of 0 0, there are points from x-axis as well as y-axis. So in each neighborhood of 0 0, there are points where f assumes positive and negative values, right? Therefore 0 0 is not a local maxima or minima, right? Okay. Now if we are given a function, then how to find this maximum point where the function occurs its maximum or minimum, right? That's we have to find. So the necessary condition is what? Necessary condition that we are taking a differentiable function, and that a differentiable function fxy have a local maxima or minima is this partial derivative is 0, right? So this is the condition, suppose 1. Now a point x naught y naught will be called a critical point critical point of f if it satisfies 1. Right. So all the critical points may not be maxima or minimum, but if it is a maximum point, it is a critical point. Right. So first we will find all the critical points. Then we will see that if it is maxima or minima. So first we will calculate all the critical points by calculating this fx equals to 0 and fy equals to 0. Right. Then there are conditions. It says now first let delta equals to this number. Since f is differentiable, we have taken, so f xy and f yx exist and they are equal. Okay, so if delta equals to this number at this point x naught y naught, right? So it is a number. Now then the first condition is if delta greater than 0 and if xx is greater than 0, then x naught y naught is a local minimum. Okay, so first we have to find this delta, and if we check this delta is greater than 0 along with fxx, then x naught y naught will be a local minimum. And if delta greater than 0 and if xx is less than 0, then it will be local maximum. Then x naught y naught is a point of local maxima. Right? The third condition is if delta is equal to 0, if delta is less than 0, then this point x naught y naught, this point this x naught y naught is neither maxima nor minima, is neither local maxima nor local minima. Okay. If delta is less than 0, it is not a extremum point, right? So for fourth, if delta equal to 0, then there is no information about this point. Okay, so you cannot say it is local maxima or minima. We have to check further, right? So then there is no information. Okay, when delta is less than 0, so it is not a point of local maxima or minima, and then it is called a saddle point. Then the point, this x naught y naught, is called a saddle point. Okay. Saddle point means the point is neither local maxima, neither local nor local minima. Okay, now we'll see some examples. to understand this exactly. So let's take this example. So classify the local extrema of the function if xy equals to okay. So you have to find all the points where the local maxima or minimum occurs, right, for this function. So first what we have to do, so first we have to find the critical points, right? So we find the critical points by doing the partial derivative and taking it to be 0, and then we have to calculate this delta, and we have to see if this one of these conditions from 1 to 4 is happening or not, right? So first we have to take partial derivative along x and y. So this is the function. So what is fx? So fx is and fy is right. So for critical values, okay, also find this fxx and fxy, all those. So fxs is fyx is same, and fyy is right. So for critical values, critical points, fx is 0 and fy is 0, right? So this implies x minus y minus x cube is 0 and x minus y plus y cube is 0. So these two implies x cube plus y cube equals to 0, right? Which is equal to so this means we'll take this two, x minus y minus x cube equals to 0 and x plus y equals to 0, okay, this one, and x minus y minus x cube equals to 0 with x square plus y square minus xy equals to 0, right? From these two, either x plus y equals to 0 or x square plus y square minus xy is 0. So these two we are getting, right? Now if we solve this one, so we'll get y equals to minus x, and if we put this in the first one, so we'll get 2x minus x cube equals to 0. So x is 0, so x equals to 0 or root 2 plus minus root 2, right? So the points we are getting is 0 0, root 2 minus root 2 and minus root 2 plus root right? Because x plus y is 0. And from this one, if we solve this, then what we will have? We'll have x square minus y into x minus y equals to 0. So x square minus y into x minus y is x cube. So it will give, so either x equals to 0 or xy equals to 1. So the only real solution is, so this means the only real solution will be, because xy, this will give x square plus y square equals to 1. Right? But 1 0 is not a solution because it will not satisfy the first one. So the only real solution will be 0 0. Okay. So these are the points and the only real solution is 0 0. So the set of all critical points is what? So the critical points are points are 0 0, root 2 minus root 2 and minus root 2 plus root 2, right? These 3 points. Now you have to check at all, is these points are local maxima or minima. So first, let's check for 0 0. For this point 0 0. So we have to find delta, right? Delta is what? Fxx fyy minus xy square at the point 0 0 now. So it is, if x's, we have already found all these 4. Now if we put these values, what will you get? We will get delta will be 0. So this will be 4 into 4 minus 4 square, which is 0, right? So it is undetermined. So we cannot say it if this 0 0 is a local maxima or minima, right? We have to investigate further. Okay, now let's look at the second one for root 2 minus root 2. For this point, what is the value of fxx? So fxx at this point is root 2 minus root 2 is at this point is minus 20, which is negative number, and delta will be, if we calculate this is a simple calculation, it will be 384, which is greater than 0. So our delta is greater than 0. This means it is not a saddle point. Now fxx is less than 0. This means it is a point of local maxima, right? So root 2 minus root 2 is a local maxima. Right? Okay, let's look at this point, minus root 2 comma root 2. So for this point, fxx is again minus 20, which is less than 0, and delta will be again 384, which is greater than 0. So this point is also a local maxima. So root 2 minus root 2, sorry, minus root 2 plus root 2 is a local maximum. Okay, so this 0 point we need to check further, right? If it is a point of local maximum, we will approach this with with the same approach we have done here in this example. Fxy is x square minus y square. So we will see two direction. In one of this direction the value will be positive, and other direction the value will be negative in a neighborhood of 0 0, right? So for 0 0, so f00 is what? F00 is 0, right? F00 on this, F00 is 0. This is 0 0. Now the function was what? Function was 2x minus y square minus, right? Now if we take x equals to y, this direction, this means this one, x equals to y. If we take this direction, if we approach 0 0, then fxx or fyy is what? This is minus 2 of x to the power 4, right? So this value is negative in a neighborhood of 0 0, right? Along this line all this functional value is negative. Now take another direction which is the x direction. X direction means y equals to 0. If we take this direction, then f x0 is what? F x0 is 2x square minus x to the power 4, which is 2x square into x square into 2 minus x square, right? Now if we take a small neighborhood of 0 0, this will be positive. In a small neighborhood of 0 0, right? Then 2 will be greater. Suppose 2 is here, 2 0, and we are taking this neighborhood, this small neighborhood, right? This is 0 2 and this is 2 0. So now we are approaching in this x axis, right? So in each of this neighborhood, these two lines are there, the x axis and this x equals to y, right? In every neighborhood of 0 0, these two lines are there, and in this line x equals to y, the functional value will be negative, and in this x direction, when y is 0, the functional value will be positive. So 0 0 can never be a local maxima or minima, because there will be some points, always there will be some points which is greater than this 0 and which is less than 0, right? So thus every neighborhood of 0 0 contains point where f assumes positive value along along y x axis when y is 0, and there are points where f assumes negative value right? So 0 0 can never be a local maxima or a local minima. Right. Since at 0 0 delta is 0, so all these conditions 1 to 4 does not give anything if it is a local maxima or minima. There is no information when delta is 0. So you have to check in other ways. Right. So here we have seen that there exist two directions. In each it is positive and the other one it is negative. So it is not a local maxima or minima. Right. So the question is done, I think. So we have classified all the local extrema of this function. Right. Okay, let's do the next question. Find the absolute maxima and minima of fxy equals to so you have to find the absolute maxima and minima of this function fxy equals to this x square plus xy plus y square over this region in the unit disk, not over the whole plane. We have to find the maxima minima only in this region. Right. So first we have to find the partial derivatives, the critical points. Right. So fx equals to 0 will imply 2x plus y equals to 0. Y equals to 0 will imply 2y plus x equals to 0. Now both will give x equals to y equals to 0. Now this gives the critical points inside this R, right? Because these definitions were in the open set, right? So for the boundary we have to calculate in different way, right? So this means 0 0 is a critical point, is the only critical point. Point in x square plus y square less than 1, right? In the open unit disk it is only the critical point. So for 0 0, what is fxx? Fxx is 2, right? And fyy is also 2. So this delta will be xy square, which is 4 minus fxy is 1. So it is 3, it is greater than 0. This means this 0 0 and fx is greater than 0. So it is a point of local minimum. 0 0 is a local minimum, right? Now we have to check for the boundary. Now let's check over the boundary. The boundary that is x square plus y square equal to 1, right? So if we parameterize this curve x square plus y square equals to 1 by, we will take xt to be cos t and yt to be sin t. So then it is followed sin square plus cos square equals to 1, right? So now our f xy will become a single variable function, right? So it is xt yt, so it will depend only on this t now. So it is what it is, it was x square plus y square xy plus y square, right? This means cos square t plus cos t sin t plus sin square t, which is 2 plus sin 2t by 2, right? So now fxy becomes gt equals to this number. Now we can check for critical points in single variable function, like we will take the derivative g dash and g double dash, right? So what is g dash t? So it is cos 2t, and we will do g dash t equals to, for critical points, g dash t equals to 0. So this will give 2t equals to pi by 2, 3 pi by 2, 5 pi by 2 and 7 pi by 2, right? So the values of t will be by 4 and 7 pi by 4, right? Now when first one, if t equals to pi by 4, right? So the point is cos t sin t. This means it is 1 by root 2, 1 by root 2, right? And what is the value of gt then? Gt will be, g pi by 4 will be 3 by 2. Okay, for t equals to 3 pi by 4, the point is minus 1 by root 2, 1 by root 2, right? And at this point the value is 1 by 2. And for 5 pi by 4, the point is both of them is minus. Point is this one, and this value g5. These are the extremal points, right, in the boundary. So we have first we will calculate this one. So this is 3 by 2, and at t equals to 7 pi by 4, the point is 1 by root 2 minus 1 by root 2, and the functional value is half, right? So what we have done here is that, so this is the unit disk, this x square plus y square less equals to 1, right? So first we have found the critical points inside this domain, right? When x square plus y square is strictly less than 1, and we have found that 0, 0 is the only critical point inside this region, right? Next we are finding the extremal points in the over the boundary x square plus y square equals to 1, and we have found that there are 4 extremal points at t equals to pi by 4, 3 pi by 4. So the points are, the extremal points over the boundaries 1 by root 2 comma 1 by root 2, this force, right? So the points will be, one will be here and the second will be here, here and here, and the other one is 0. 0 is inside this all these 5 points are the extremal points, right? Not extremal points, they are critical points. They can be maximum or minimum, right? So at this point we have found the value, functional value. The first one is 3 by 2, 1 by 2, 3 by 2 and 1 by 2, right? So the, and at 0 0 it was at 0 0 the value was f00 is 0, right? f00 is 0. I have not written that, I think f00 is 0. So these 5, so the maximum is what? From this 5 the maximum is 3 by 2 and the minimum value is 0 0, right? So the maximum occurs, so hence fxy attains its absolute maximum value, which is 3 by 2, at 3 by 2 is attained at the point minus 1 by root 2, 1 minus 1 by root 2 and 1 by root 2, 1 by root 2, right? Then at 1 by root 2, 1 by root 2 and right. Also it attains its absolute minima absolute minima 0 at the point 0 0, right? So it has attained its maximum value 3 by 2 at this 2 point and minimum value at this point 0 0, right? Okay, we'll see another example. So a rectangular box open at the top is to have a volume of 32 meter cube. Okay. Then what is the dimension? Then what must be? Then what must be the dimensions so that the total surface is minimum, so that the surface so a rectangular box is given and the volume of this box is, it is open in the upper, it is open lid, right? Open at the top. Now the volume of this rectangular box is 32 meter cube, right? Now what must be the dimension, that is length by width and by height, so that the surface area is minimum with this volume 32 meter cube, right? So let's look at the box. So this is the box, right? Okay. Now this one, this is x direction, this is z, and this is y. Okay, and the volume of this rectangular box is 32 meter cube, right? So xyz, let xyz are edges of this box. Right? Now what is the volume? Volume is V, which is the formula is xyz, right? And surface area is what? Surface area S is, since it is open on the upper open lid, so the surface area will be xy plus 2yz plus 2zx. So this xy is not counted twice, right? All the other are counted twice. So this is the surface area, and we are given that xyz equals to 32, right? So this means our z is 32 by xy, right? So we have to minimize what? We have to minimize the surface area S. Now S will be a function of, so x is xy plus 2y, z will put the value of z, xy plus 2x 32 by xy, and this will be xy plus 64 by x and 64 by y, right? So this is xy, and we have to minimize this one, right? We have to find the minimum value of sxy. So in the similar manner, we'll do the partial derivative. So sx is y minus 64 by x square, sy is y square, right? So we'll put this 2 to 0. So this 2 will imply x square y equals to 64 and xy square equals to 64, right? So this will give x, if we divide this 2, then we'll get x equals to y, right? So this will imply x equals to, from this equation, x equals to y equals to 4. This means z equals to 32 by xy, which will give 2. So we have the value x equals to 4, y equals to 4, and z equals to 2. So this is the dimension, right? Dimension means length by width by the height. So if this box, rectangular box, is of this dimension, then it gives the minimum. Okay, I have not calculated if it is the minimum or maximum. We have found this point. Now we have to calculate this delta, right? Okay, so first we have to find this sxx, which is what? This is 128 by x cube, right? And syy is this y cube, sxy is 1 and syx is 1. right? So at this point, this at 4 4, this point xy, this 4 delta equals to sxx syy minus sxy square, which is minus 1, right? So if we put x and y to be 4, so this will be at this point x equals to 4, y equals to 4. So this will be greater than 0. Okay. Right? So delta is greater than 0 here, and sxx is 128.54q, which is also greater than 0. So this point 4 4 is a minima, is a local minima of sxy, right? So we have found this 4 4 is a minimum point. So this means, and when xy is 4 4, z is, we have found that z is 2. So this means the dimension should be 4 meter by 4 meter by 2 meter to give minimum surface, right? So the dimension should be minimum when the value the dimension, if this dimension is this 4 by 4 by 2, then the box has minimum surface area, right? Okay, so in this session we have discussed about partial derivative and directional derivative and maxima minima of two variable functions, right? In the next session we will discuss about the double integral. So I will end this session here. Thank you.